In section 7.7, we're going to take a little bit of a different approach to integration. And in these problems, we're always going to be working on definite integrals, which means we have bounds we want to plug in after we find our antiderivative. At this point here in Chapter 7, we probably feel like we've learned how to integrate pretty much everything, but there still may be things that we are unsure how to integrate, and certainly we can't remember how to integrate absolutely everything. So if we're ever faced with a definite integral that we aren't sure how to integrate, there is a way that we can do numerical integration to at least get a pretty good estimate of what the answer is going to be. Numerical integration is also good if we don't actually have a function though, but we have tabular data, which means data is given to us as a set of points and not a function. So we're just given kind of a set of XY coordinates, and we're told that these coordinates make up a function. And that's actually very common in real life applications. If somebody were to just take measurements of, say, the depth of a pond at certain locations. So we could say X is the horizontal location, and then Y is the depth. We might not be able to model a function after that, but we could at least set that data up in a table, and we can use that data to integrate, do at least numerical integration, even when we don't have a function. There are several different methods for numerical integration. I'm just going to focus on the midpoint rule, but if you look in the textbook, there's also a trapezoid rule and a Simpson's rule. The basic idea is exactly the same. They just make different shapes is all out of the area under the curve, and you'll see what I mean when I draw a picture here. So let's say we were asked to integrate some function from a to b, and we just wanted to do like an estimate using numerical integration. So here's our function. And we will just call those A and B. So back from Calculus 1, hopefully you remember that a definite integral will give us the area underneath that curve, or the area between that curve and the x-axis. If f of x is something that we recognize how to the antiderivative for, we could easily just find the antiderivative and plug in our endpoints and subtract and find the exact answer. But if f of x is something we don't recognize how to integrate, or if f of x is given to us as tabular data and not a function at all, we might not be able to integrate that thing at all. So another option is to break this region up into subintervals. And how many subintervals is just dependent upon the problem and dependent upon how accurate you want your answer to be. In the problems that we're going to do, we'll always be told how many intervals to create, and we will call that n. So n equals the number of subintervals. So with the midpoint rule, what we're going to be doing is calculating the area of these rectangles. Well, right now they don't look like rectangles, right? Because the top of each of them is curved. So what the midpoint rule says is we're going to use the midpoint of each of these subintervals as our height. So we're going to follow up the midpoint and use that as our height and make a rectangle out of that. Because usually one side will be a little bit higher and one side will be a little bit lower, and they hopefully the excess on one side will cancel off the deficit on the other side, and it should be a pretty accurate, it'll be a pretty accurate calculation if we use midpoints. So you'll see when I'm drawing these horizontal green lines, on the left they're going above my function, but on the right they're below the function. So that's what I mean where there's an excess on the left, but there's a deficit on the right, and those should cancel each other out. They're not going to cancel each other out perfectly, and this answer we get is not going to be exactly the same as what we would get if we did this theoretically with our integration techniques. But like I said, we can't always use our integration techniques. This might be a function that we don't know how to integrate, or it might be tabular data, so we don't even have the option to integrate a function. So we're going to call these m sub 1, m sub 2, m sub 3, m sub 4, m sub 5, m sub 6, m sub 7. So I split my region up, or I split my interval up into 7 subintervals. And I found the midpoint of each of my subintervals. Now the height of each of my rectangles here, the height always just goes up to the function. So the height is just the functional value at the midpoint. So to figure out our estimate using the midpoint formula, we would call this m sub 7, because I'm using the midpoint rule with 7 subintervals. I'm going to first figure out how wide those rectangles are. That is called delta x. Delta x is usually just a little width of x. So what I've done is I've taken my entire a to b interval and I've split it into n subintervals, equal subintervals. So a quick calculation for the length, or excuse me, the width of each of those rectangles along the x-axis is b minus a divided by n. So the a and the b we're getting from the original integral, and then the n is the number of subintervals that we're wanting to break it up into. That will give us the width for each of these rectangles. So remember, the area for a rectangle is, for these would be width times height. So I've got b minus a over n. That's the width for one of my rectangles. And then I need to multiply it by the heights of each of my rectangles. So for my first rectangle, my height is the functional value at my first midpoint. For my second rectangle, it's the functional value at the second midpoint, and so on until we get to our last midpoint. Now I've got all of my my heights grouped together because technically we could do this one at a time, but they all have the exact same width. So what I've really done is I've just factored that width out once to the front. Now this is not going to give us the exact same answer that the integral gives us. So once we actually go through an example, we'll talk about the difference between the two. It's got a special name, and it is a good thing to consider what the difference is. There is an error involved in doing numerical integration. So we're going to use the midpoint rule with n equals 6 to calculate the integral from 0 to 3 of x over x squared plus 2 dx. Now we can integrate this one by hand, but we're just going to go ahead and do a numerical integration. I wanted to pick one that we could do by hand. That way we could compare the exact answer with our approximate answer. So let's take a look at what this graph looks like. I want to do this one as accurately as possible. And we're only considering the interval 0 to 3. This graph does not have very much height to it. I'm going to mark 0 there, and 1, 2, 3. If you plug 1 in to your function here, f of x is x over x squared plus 2. And we're going from 0 to 3. We were told that n equals 6. You could go ahead and just plug some values in to help you get a graph. It might be good to actually know some of those functional values. We might need them later to do our calculation. If you plug, let me go ahead and plug 0 in. If we plug 0 in, we get 0, because we'll have 0 over 2. If you plug 1 in, you're going to have 1 over 3. And then after that, it just keeps getting smaller. So I'm actually going to put 1 all the way up here, and then a half, a quarter, 3/4. So a third is about here. We'll say if you plug 2 in, you're going to have 2 squared is 4, plus 2 is 6. So you're going to have 2 over 6, which is also a third. So there's like a little hump in between there. And then if you plug 3 in, 3 squared is 9, plus 2 is 11. You've got 3/11ths, which is less than a third, but more than a quarter, because a quarter is 3/12ths. Oops. So, not the most beautiful graph, sorry about that. So we want to know, and we're going to cut it off at 3, we just want to know this area here, this area in the middle, from 0 to 3. And we're going to do it by breaking it into 6 subintervals. So you can figure out your delta x. Remember, that is b minus a over n. So we've got 3 minus 0 over 6, which ends up being a half. That means we're going to cut it at every half of a unit. So we're going to cut it at a half, and then at 1, and then at 3 halves, and at 2, and at 5 halves, and at 3. And if you count, we'll have 6 sections in there. For the midpoint rule, we want to know the midpoint for each of these little sections we've just created, and we're going to use the midpoint as the height of our rectangle. So we have more calculations to do before we are ready to do our area. So the way that you find a midpoint is just an average. It's just the average of the two values that are to the left and to the right of it. So that's why I labeled all of those little sections that I just cut my interval into. So my first midpoint is exactly halfway in between 0 and 1/2. So the way that we figure out the middle is we add them together and divide by 2, which ends up being a quarter. So this is like midpoint, first midpoint, m sub 1 is a quarter. And then after that, because our delta x is a half, after that they're all a half a unit away from each other. You also could just keep doing the same thing. M sub 2 is the midpoint of the second rectangle, which is halfway in between a half and 1. So a half plus 1 divided by 2, you end up getting 3/4. And we're going to do the same thing over and over and over again. But you'll notice when you calculate each of these, they're all exactly half a unit apart. That's because all of our rectangles are half a unit wide. So our midpoint estimate, when we break this up into 6 rectangles, well, all of our rectangles are a half a unit wide. And to get my height for my rectangle, I'm finding the function value at the midpoint for rectangle 1 we said was 1/4. The midpoint for rectangle 2 is 3/4. The midpoint for rectangle 3 is going to be halfway between 1 and 3/4, or excuse me, 1 and 3/2, or it's also going to be exactly a half more than 3/4, which is going to be 5/4. And then we'll have, the next one is 7/4, and 9/4, and 11/4. And you should probably go ahead and confirm this for each of them. This is the point right here, and this is the point, oops, this is the point right here. Now I'm not using 1/4 as my height, I'm just using 1/4 as the location on the x-axis that I'm using to find my height. So now I need to take those x values and plug them back into my function. Remember, the function was x over x squared plus 2. So now we need to figure out all these function values and add them together and then multiply by 1/2. So let's take a second to do that. And this is not going to come out very pretty. So I'm going to go ahead and pause the video for just a second and plug some of these in. So all I've done is I have plugged in 1/4 into my function x over x squared plus 2 and changed it back to a fraction and got 4/33, and then plugged in 3/4 into x over x squared plus 2 and I got 12/41. Then I plugged in 5/4 into x over x squared plus 2, I got 20/57, and so on. So I've got all of my functional values here. These are the heights for all of the rectangles when we use the midpoints. So now we just need to add them together and then multiply by 1/2. And I'm going to go ahead and I'll write an exact answer, but then I'm also going to write a decimal. Well, it actually turns out that the denominator on this fraction is so huge that my calculator does not want to write it as a fraction. So we are going to just write an approximate. So I got 1/2 times 1.71661702.4. So the 17166, that's just the value in the parentheses. And then the width for each of these rectangles was 1/2. So my final answer for my approximation using the midpoint formula is about 0.858308512. And I'm just writing down all of the decimals that my calculator will show. So 858308512. And I'm using all of those because I want to compare it to what the exact answer is. This is our approximation. This is our midpoint approximation. So this is what we were asked to find. And there are some problems where this is all we can do is find an approximation. And sometimes this is going to be a really, really good approximation. Sometimes it's not going to be that good. The more rectangles you break your area up into, the better an approximation it's going to be, because these pieces right here will get smaller and smaller. So those pieces with the excess will get smaller, and those pieces with the deficits will get smaller. So these pieces will get smaller and smaller as our rectangles get skinnier and skinnier. And those rectangles will get skinnier if the number of subintervals that we use gets larger and larger. So if I was to break 0 to 3 up into 100 pieces, there would be definitely less and less overlap outside of the region, or deficit being excluded inside of the region. But obviously, you would not be able to sit here and do 100 rectangles by hand. At that point, we would use a program, or we could easily write a program in Excel to do something like that for us. What I want to do now is I want to compare this to the exact answer, because this value has error in it. So there is something called absolute error, and there is something called relative error. So absolute error is just the difference in the exact answer and the approximate answer. And the way that our book likes to write this, it says, suppose C is a computed numerical solution. So a numerical solution is something you get without any calculus, like the rectangles we just did, the midpoint rule, the midpoint formula. So C is going to be the approximate answer. So suppose C is a computed numerical solution. In parentheses, I'm going to put approximate. To a problem having an exact solution X. So C is our approximate, X is our exact. Absolute error, this just tells us how far off our approximate is. It's the absolute value of C minus X. The reason we do absolute values is because we don't care really if our approximate is larger or smaller. So the absolute values just kind of disregard the negative symbol in this subtraction, and it just tells us how far away from the exact answer we are, and it disregards any negative symbol. The other really important one, sometimes absolute error does not tell the whole story. So this absolute error can come out to be 1,000. And you can think, oh my gosh, I'm off by 1,000. That is huge. I've done something completely wrong. But that might not be the case. Absolute error doesn't always tell the whole story. There's something else called relative error, which is, in my opinion, is a lot more important. Relative error takes your absolute error and compares it to what the area is supposed to be. So it puts it in perspective. So it takes that giant error of 1,000 and says, well, if the error was supposed to be 1 billion, then really being off by 1,000 is not that much. Well, if your area was supposed to be 1,000 and you're off by 1,000, then yeah, the value of this fraction is 100%. You're off by a lot. But if you're off by 1,000 on 1 billion, that is a tiny amount. So the relative error puts our absolute error into perspective compared to what the exact answer was supposed to be. Now this is only going to work if area was not 0, obviously, because we can't divide by 0. So I told you just a minute ago this problem was actually one that we could calculate by hand. So we're going to go ahead and calculate this one by hand and do the absolute and relative error. We can integrate x over x squared plus 2 from 0 to 3. That's just a u substitution. And the way that I recognize that is because the denominator is a quadratic, the numerator is linear. So I could easily do a u substitution for the bottom, and my du will get rid of my linear numerator. It will, however, introduce a 1/2, an extra 1/2 coefficient. Oops, got extra u's there. Those should be x's. So my x dx is going to get replaced with a 1/2 du. So we could rewrite this as 1/2 of 1 over u du, which turns into 1/2 natural log of u, or 1/2 natural log of x squared plus 2, evaluated from 0 to 3. And we get 1/2 natural log of 11 minus 1/2 natural log of 2. Well, no wonder we couldn't get a fraction, because this value is nowhere near a fraction. It's got logs in it. So let's see what the calculator has to say about this. So when I type this into the calculator, I'm getting 0.8523740461. This is our x. This is our exact value. Now earlier, for our c, for our approximate value, I'm going to pull that value down because we're going to need it. I just want it in a more convenient spot. We had 8308512. Right next to each other, doesn't look so bad. They both have 8500ths, that's good. It's not till we get to the thousandth spot that they diverge. So the exact answer has 2 thousandths, our approximate answer had 8 thousandths. So our approximate is a high estimate. It's a little bit too big. But let's actually do a calculation of how far off we are. So absolute error is c minus x. So I'm going to do my c value minus my x value. And I've got 0.00, and I'm just going to round this one, 6. 0.006 is about how far we're off by, about 6 thousandths. And then my relative error, we really have no idea if 6 thousandths is good or bad until we compare that to what the area under that graph was supposed to be. So relative error is your absolute error divided by what the area was supposed to be. So this is going to be 0.006 divided by what the area was supposed to be, 0.852374. And I got 0.00, and again, if we just round it, it's about 0.007. It's also common, so relative error is 0.007, but it's also common, and I'm going to write this in red, to think of this as a percent error and move the decimal point 2 spaces. We're not even off by 1% on that value. We're off by 0.7%. So that's really good. We got a really good approximation. We're off by less than 1%. And if we were to break it up into even more subintervals, our approximation, our value for C would be even better. So just by breaking it up into 6, we got a really good approximation. So if we were to break it up into 10 or 12 or 50 or 100, we would get an even better approximation. And actually the definition for a definite integral is what would happen if that number of subintervals went to infinity or the width went to 0. And those two ideas are the same. There's also some other types of numerical integration that can be done, and they give slightly better approximations than the midpoint rule. There's something called the trapezoid rule. And you do exactly what it sounds like you're going to do. Instead of making rectangles, what you're going to do is you're going to make trapezoids. So if you have this function f of x, and you want to estimate the area numerically, instead of just picking the midpoint, what you're going to do is you're going to connect the endpoints and create a trapezoid out of it. So you see that first one is going to have a little bit of excess area. The second one has a little bit of deficit. The third one has a little bit of deficit. I didn't split it into very many rectangles, but obviously if you use, or not trapezoids, but if you use more trapezoids, that amount would be minimized. So instead of using just length times width for that formula, the formula is just slightly different because it uses area for a trapezoid, which is area equals base 1 plus base 2 divided by 2 times height. Now, in order to think of this thing as a trapezoid, we actually have to turn them and look at them from the side. The height is actually our delta x, and the base 1 and the base 2 are the function values at our endpoints. So we'd have like f of x0 plus f of x1. And this would be the area of our first trapezoid. And then we would do that for each of the trapezoids. What ends up happening is all of those middle boundaries are going to get used twice, because this boundary right here is the right endpoint on your first trapezoid, but then it's the left endpoint on your second trapezoid. So the trapezoid formula, we would call it T sub n. You use delta x, because that is the height for our trapezoids. And then we just go ahead and pull that divide by 2 out. So I'm going to say delta x over 2. And in the parentheses, we've got our initial point, and then we're going to have 2 of each of the intermediate points. But then we're only going to have 1 of the end points. So we just have 1 at the very beginning and 1 at the very end, but then we have 2 of all those intermediate points because they serve as the right boundary of the trapezoid before it, and then the left boundary of the trapezoid after it. So the trapezoid rule is just another type of numerical integration. For this homework, though, I think we just stick with the midpoint rule. So you can just work with the midpoint rule for all of your numerical integration problems in section 7.7. There's also the Simpson's rule. It's very similar to the midpoint rule where we've got some different coefficients on our function values. It just mixes up the coefficient values between, I think, 4s and 2s instead of all 2s. And then it has a divide by 3 in the front. And that one is even more accurate.